Hello everyone, welcome to my YouTube channel. My name is Jorge Morales. I'm a research scientist actually working in Germany. And for today's video, I'm going to show you how to accelerate your Abaqus simulation time with just one click and one command. So please stay in the video if it is interesting for you, and see you now. We are going to activate this. It's very easy, and I will show you two ways for this video. One in the graphical interface of Abaqus KAE, in the simulation service of Abaqus KAE graphical interface, and the other one in the terminal or in the console, as you want to. Maybe you are using Linux, or you have no access to the graphical interface of Abaqus if you are working in a remote server. So we can take as well usage of the GPUs by means of the terminal in order to run the jobs. So how we are going to do this in the first time is for the graphical interface. When we are creating a new job, this is very important. When we are creating a new job, we can right click, create a new job, or we can just double click, and then let's give a name, tutorial GPU, and then continue. And here, this is the most important thing. In the job pop-up that just came out here, we are going to go to the tab parallelization, and then we are going to activate. First of all, we want to activate the multiple processors. As we know, Abaqus is able to use advantage of multi-processing capabilities in our machine. So for this case, just for an example, let's take 8 parallel processors. This depends what you have in your computer. Then let's activate the GPU Acceleration. What is GPU? This is general purposes graphics processor unit compute, no? And depending on the graphics card that you have, how many graphics cards you have installed in your computer, you are going to change this number. Usually most of the people have only one GPU installed in their computer. If you have multiple GPUs, you can increase this number. For my test and for my research and for my experience, I have tested many graphics cards from AMD, from Nvidia, from AMD, and I can always recommend, by my experience and by the test that I since today made, I can always recommend use Nvidia graphics cards that are capable of double precision capabilities, or that had enough compute precision capabilities, double precision compute capabilities. Let's just activate this and use. This is the main thing. Just activate here the GPU Acceleration, and then let's click OK. And that's all for the graphical interface. That's all. And then I will show you now how to activate it in the terminal. But for the graphical interface, this is everything that you need to do. There is nothing else to do. Then you can just submit the job, and it's going to take immediately advantage of the graphics card acceleration capabilities of Abaqus. So now, in order to activate the GPU capabilities from the terminal, when we are running to our job, let's first of all, as we said in the tutorial before, let's first define our working directory. So we're going to do this. We are going to go to File in Abaqus, and then set work directory. And then, for example, I'm just going to define here in my desktop one folder that I made for today, and then click OK. And now the working directory is being created. After that, the job that we already created is still in the graphical interface. We're going to right click and then write input. This is going to generate an input file in the working directory. And then you can save this, and then you can already close the graphical interface of Abaqus. We don't need it anymore if we want to run the job in the terminal. So let's bring now a terminal here, and then let's define here our path. Let's go to our path in desktop, and then tutorial GPU, and if we take a look, we have only here the path. We have actually only the input file that we just generated. So in order to run the job in Abaqus, with the GPU, let's do the next command. is Abaqus. You are going to call this. If you have some errors in order to call the software, then you need to take a look to the environmental variables or to the system variables of your system when you installed Abaqus. But if you install it by default in Windows, you should have no problems. So Abaqus, and then we need to define the job name. The job name was tutorial GPU, I guess. Otherwise, there is no problem. This is going to generate a different job name. And then the important thing here is the input file that we generated. And then we're going to head in at the input, and it's going to be tutorial gpu.imp. And then we need to define the CPUs that we are using. In this case, just an example, we're going to use 8. And then we need to define the GPUs. This is the most important thing to activate the GPU computation capabilities of our system. We are going to define here one as an example. And then I always like to activate this also, this command also. This is not, and sometimes if you are working locally in your computer and you are connected to the license servers, usually you are connected to license servers when you are using Abaqus, or if you are using the student license, you probably have it locally install the license. But if maybe you already sometimes get some problems because license is not connected to the license after some times of idle the software, I always use this command in order to not have problems with this idle time and lose the license during simulation. And then this should do the job, and then let's just press enter, and it's going to start running the job. And this is how do we do it in the terminal. The main command here is this GPUs equal to the number of graphics cards that you are using, and the job tutorial and input name needs to match to the one that we created. And let's go now to the results, to the benchmark results, to see how it really affects the use of GPU for our simulations. Okay, so for this video, I made two benchmark samples. The first sample is based in a 1.44 million degrees of freedom component, and the other one is based in a bigger model, medium bigger model with around 5 million degrees of freedom. Why this is important, we're going to see now. So as we can see here, for the first sample with 1.44 million degrees of freedom, okay, by the way, I am using Abaqus 2018. I have a machine with two sockets. It's a Xeon E5 2699B3, and this is the most important thing for this video, I have two Nvidia Tesla's K40s. The Nvidia Tesla's K40, they have 12 gigabytes of GDDR5 memory, and they have 2888 CUDA cores, and they could output a compute performance of, in double precision, of 1.72 teraflops. Why this is important? Because usually Abaqus takes advantage of high double precision compute capabilities graphics cards in order to make its job. I can always recommend you, from my experience, since I made a lot of tests with AMD as well with Nvidia graphics cards, and to be honest, after my whole experience, I can only recommend you to use Nvidia graphics cards. OpenCL is also accepted for Abaqus. Abaqus can compute as well in AMD graphics card, and usually is also very good performance. But because of drivers stability and this cooperation in between Nvidia and Dassault systems and Abaqus, this is why I always can recommend use Nvidia certified graphics cards for Abaqus in order to use the GPU acceleration capabilities. In my case, I have two graphics cards, Nvidia's Teslas. So as we can see here, the CPU only is this black chart, and when we only compute with 4 physical cores, we made around 72 minutes in order to have the solution time. So this is very important, because if you see here, when we use 8 cores, we reduce the solution time to 48 minutes from 72. when we use 16 cores, we reduce the computation time to 42 minutes, and for 32 cores, we reduce the computational time to 32 minutes approximately. We can see that for this small medium model, the scaling of, for example, doubling the CPU cores doesn't improve to half the performance. Yeah, we're going to speak about this later. And here the important thing, as we can see, for a small model, the use of 4 CPU cores together with 1 graphics card, it can improve dramatically the performance. We can see here that we reduce our computational time from 72 minutes with CPU only to 33 minutes using 1 graphics card. This is amazing, really. If you are a student, if you work in the industry, or if you are a researcher, you know that it's not the same thing to wait for more than 1 hour in order to get one solution, to wait 30 minutes. There is a huge difference in this. And then if we see for the next example with 8 cores, we reduce our solution time from 48 minutes to 26 minutes. This is a gain of up to 1.8 times. For the 16 cores, we reduce as well dramatically our solution time from 42 minutes to 22 minutes with a speed up of 1.9 times. And then if we see here for the 32 cores, we only improve our performance around 1.3 times, from 32 to 25 minutes. What does this mean? Does it mean that with lower cores you can do a better job? Not precisely. This is because this is a relatively small model. 4 cores is enough in order to parallelize in a good way all the operations that we are transferring to the graphics card. But after this benchmark as well, I could say for a small model, a small medium model up to 2-3 million degrees of freedom, the sweet spot is to use around 16 to 8 cores, around 16 to 8 core machine to use with 1 graphics card. This improves insanely the solution time and the performance of the simulation time. This is the sweet spot. 16 cores, I think this is the best option for a small medium models. The other shots we are going to talk about in the next sample. So the next example is a model with 4.5 million degrees of freedoms. It was made in exactly the same machine. There is no variables in the machine, and here we can see that with the 4 cores CPU only solution, we took around 415 minutes. These are around 7 hours. 7 hours to compute a solution. This is one job day. This is a one whole job day, and we can see how dramatically increase the solution time or decrease the solution time. Sorry, from 415 minutes to 192 minutes. This is a 2.1 improve in performance compared with only the CPU solution. We can see when we use 8 cores, it scales better than the 4 small models, and then we improve our solution time to up to 2.4 times, from 282 minutes to 119 minutes. And then for the 16 core solution, we improve from 238 minutes to 91 minutes. This is a 2.6 times in performance improvement. And then here this is very interesting. We can see that with 32 cores, we went from 146 minutes to only 124 minutes. The improvement here by using 1 graphics card was not really relevant. Still an improvement, but not so significantly as in the other ones. Here we can see that the scaling is better for a bigger model, from 4 cores CPU only to 8 cores to 16 cores to 32 cores. Why? Because here in this case, when we have many cores as 32, the discretization of elements is distributed in a better way in order to make the operations. So you have always something to do. The CPU cores have usually always something to calculate. This is why the performance improves in a better way. It's not perfectly scalable, but improves in a better way. What we see here is that when we take 16 cores and the use of the graphics card, of one graphics card, the performance improved here for 16 core is amazing. It's 2.6 times. It's almost 3 times improved in performance time. This is because the amount or the ratio of distribution between the operations that handles the CPUs and the GPU it's more structured. It's in a more structured way in which the GPU can reach peak performance in order to compute in a more stable way and transfer back the solutions to the CPU. That's why with bigger models, it doesn't mean that you need a bigger model in order to get a solution. But with bigger models, you have more operations to do. And these more operations means that the graphics card, as I said, can reach peak performance and then compute more stable. So I can recommend as well, from my experience, that as well after this benchmark, one very good sweet spot to configure your computer if you're looking for a new computer is to have at least 16 cores, 16 physical cores in your computer and at least one graphics card. Let's talk now about the third chart that we have here. Here is with the CPU plus 2 graphics cards. We can see that the improvement when you use a small amount of cores is still an improvement, but price performance maybe it's not very suitable to spend a lot of money or more money in a graphics card when you have, for example, with 8 cores. We can see that there is no improvement in performance. Actually, it worst. 1 minute worst. 1 minute took longer to get the solution, and here also worst, and here it's also worst. What does this mean? As I just said before, the operations distribution of Abaqus is really not well distributed, and the graphics card, they really not reach performance because there is no enough operations. But in this case, I did not prepare bigger model samples of benchmarks, but I can assure you that if you use around, I don't know, maybe 10 million degrees of freedom models, higher large models like 20, 40 million degrees of freedom, the scaling of graphics card can really improve the performance. But for these small, mediums, a little bit big models, the use of more graphics cards do not really improve the solution time for Abaqus. So yeah, and let's take a look now a little bit why this is happening, why this improvement in performance is happening. So how Abaqus take advantage of the GPU? Abaqus is based in something called a supernode based direct sparse solver. The solver is the main engine that is doing the calculation in background for the software, and this scheme is usually based in an elimination tree that is built in Abaqus, and then this elimination tree is built for the sparse solver, and then the nodes in the tree, those are matrices, usually dense matrices, and then the factorization of the sparse matrix is based on the factorization of those dense matrices, usually called frontal matrices or front matrix, and their assembly into supernodes, in these Abaqus supernodes that they are calling. And the thing is, most of the runtime of a direct sparse solver is spent in this factorization of frontal matrices and their assembly. So the typical strategy for developing a direct sparse solver for the GPU is to take all those dense matrix operations to the GPU, and this can be really, then this architecture can be very well optimized for large scale GPUs. And Other solver operations such as the matrix assembly, tree traversal, forward, backward solves, all can they stay in the CPU. The CPU usually take these other operations and do it by itself, and then only those dense matrix factorizations are sent to the GPUs. And this is how you improve the solution task, because this factorization is very computational intensive for the CPU only to work. But if you offload those intense operations to the GPU and to the many thousand GPU cores that you have, this is how you improve really your performance. Why do you have bottlenecks when you have small models? It's because these dense matrix are really small, and it takes more time to send the information to the GPU core from your CPU and take the information back. What this takes more time? These are like picoseconds. These are really small amount of time, but maybe it takes more time just in the sending operation than in the job that it's doing. And the GPU is not reaching peak performance, which means it's not really computing in a very stable way. It's just taking something and then very fast, and then it needs to transfer it back again, which it takes time already. And this is why small models, they really don't take advantage of GPU acceleration. As I said, around 600,000, 1 million degrees of freedom is a sweet spot to start to take advantage of GPU acceleration, because this dense matrix is big enough to be parallelized in so many computational cores. Why do I say this? Maybe this is not interesting for you, but I think it's always a good practice for a research scientist or for an engineer to get to know a little bit of why this is happening. It's not only about click, GPU acceleration is activated. This is very good. This is very good because usually in the industry you have no time to take this. But at least if you take 1 to 3 minutes from this video to have a small idea why this work, I think it worth it. And if you like this video, please get subscribed. If you 1 like in the video is also very good, appreciated. And I hope this help you in your research, in your studies, in your career. And thank you very much, and see you in the next video.